Everyone. Now we are going to learn safety and resource request algorithm, which we are going to apply for banker's algorithm for deadlock avoidance. Learning outcome of this session are: at the end of this session, student will be able to explain safety and resource allocation algorithm required for banker's algorithm. Now let us see safety algorithm. Safety algorithm is used for finding out whether or not a system is in safe state. Now the pseudocode, we will first see the pseudocode of this safety algorithm. So the step 1 is consider work and finish as a 2 vector of length m and n respectively, means work has a length m and finish has a length n. Then initialize work equal to available and finish of I equal to false. This is the initial value. Work will be equal to available and finish of I will be equal to false for all I. That means I equal to 0 to n minus 1. Okay? And this I is for process Pi, P0, P1, P2, P3, P4 like that. Okay? So initialize work equal to available and finish of I is equal to false. Then we need to find an index I such that both finish of I is equal to false and need of I is less than equal to work. Means for particular process, finish of I is equal to false and its need is less than equal to work. Now what is work? Work is nothing but the available. Means here we wish to check the need of the process is less than available or not. Less than equal to available. Okay. If no such I exists, then go to step 4. Means we are trying to find out the process whose need is less than currently available resource. Okay. But if no such process, we don't get any such process, then we have to go to step number 4, and that step number 4 is we have to mark that finish of I is equal to true. But if we find the process whose need is less than available, then we have to add or we have to allocate the resources which are needed by that process, and then after allocating we have to update the work. Work will become work equal to work plus allocation and mark finish of I is equal to true. Okay. And if no such I is there whose need is less than available, then we have to mark finish of I is equal to true. And if all these, if we pass with all the processes in the system, then we can say that the system is in safe state. Okay, system is in safe state if we found at the end finish of I of all the processes equal to true. Okay. Means here in safety algorithm we are checking that whether need is less than available. If need is less than available, then we are allocating the resource of that process to it, and then we are modifying the work vector. Okay. So just think that how many number of operations will be required to determine the safe state using this safety algorithm. Yes. So here this algorithm require an order of m into n square operations to determine whether the system is in safe state. M is nothing but the number of resources and n is nothing but the number of processes in the system. Okay. That is what about the safety algorithm. The next is resource request algorithm. Now for banker's algorithm to apply for deadlock avoidance, we require safety algorithm and resource request algorithm. So first we have to check whether system is in safe state or not. If we found that system will be in the safe state, then we can go for this resource request algorithm. So before applying resource request algorithm, first check whether system is in safe state or not using safety algorithm. So this resource request algorithm is used to determine whether request can be safely granted. Okay. Now using safety algorithm we can find whether the system is in safe state or not, but after that we have to check whether the request made by the process can be safely granted or not. So let us consider request of I be the request vector for process Pi. If request I j is equal to k, means process Pi. Now this request of I is what? This is the request for process Pi. As here we have subscript I. This is the request for process Pi, that Pi wants k instance of resource type Rj. Okay. So request I of j is equal to k means process Pi may want k instance of resource type Rj. So when a request for resource is made by process Pi, then it has to take some actions. So whenever this request is made, then first it has to check whether the request made by that process is less than or equal to need. Okay. First it has to check the need of that process. The request made by the process is less than its need. If yes, then go to step 2, otherwise raise an error condition since the process has exceeded its maximum claim. Means if the request made by the process is not less than need, means what? The process is requesting more resource which is not mentioned earlier. Okay. So so the operating system have to raise the error condition. Okay. But if request of I is less than equal to need of I, then go to step 2. The step 2 is check whether that request of I is less than or equal to available. First check that request made by that process is less than its need. Then second, if yes, then check whether that request made by the process is less than equal to available number of resources. If yes, then go to the next step. Otherwise again, if it is not less than available, then that process has to wait, since that resources are not available, and it has to wait till other process releases that resource. Okay. So that is the second step. Now if request made by the process is less than available, then pretend have the system pretend to have allocated the requested resource to process Pi by modifying the state as follow. Means if both conditions are true, request is also less than need, request is also less than available, then system must pretend that if we allocate these resources to the process, then and it will try to modify the state of the process and check whether that system results in safe state or not. So how it will do this? So here first it will modify available matrix. So if it wish to allocate that resource, then it has to change available matrix. Available will become available equal to available minus request. Okay, because that request are allocated, so automatically it will be removed from the available. Then allocation is equal to allocation plus request, because along with previous resources, new resources are requested by that process are allocated. So now allocation becomes previous allocation plus current request, because they are now allocating these resources to the process. And then need equal to need of I minus request of I. Again need will become less, because need will be subtracted. So need equal to need of I minus request of I. That will be done. Okay. So these changes will be done by the operating system. Okay. And if after doing this, if the resulting resource allocation state is safe, then the transaction is completed and the process Pi is allocated to its resources. Okay. So first it has to check whether the request made by the process is less than need, whether it is less than available. If both conditions are true, then it has to subtract the request from the available, then it has to subtract it has to subtract it from the need, then it has to subtract from the need and find out now the remaining need of the process, and also it has to add it into the allocation. Okay, that is done by the operating system, and after that it has to check whether that system is in safe state or not. And if it is in safe state, okay, then that resources will be allocated to the process. If it is in not safe state, then if that state is unsafe, then that process must wait for the request and the old resource allocation state is restored. Means old resource allocation state is restored means what? Here whatever these modification is done by operating system, all these will be restored. Okay, this is not done if they find the unsafe state of the system after allocation of the resource, and process P must wait. Okay. Now consider one example here. Suppose we have 5 processes P0 to P4 and we have 3 resource types. Resource type A which has 10 instance, resource type B which has 5 instance, and resource type C which has 7 instance. Okay. And then at time T0, this is what the allocation and matrix of the process. Okay. So as we can see here, we have process P0, P1, P2, P3, P4, and now A has total 10 instance. From that 10 instance, 2 are allocated to P1, 3 are allocated to P2, 2 are allocated to P3. So 2 plus 2 4 plus 3 7 are allocated. So out of 10, 7 are allocated. So how many are available? 3 are available, right? Then process B has 5 instances and C has 7 instances. So from 5 only 1 and 1. 1 is allocated to P0, 1 is allocated to P3, only 2 are allocated, so remaining are 3. And from C has total 7 instances. From 7, 2 are allocated to P2, 1 is allocated to P3 and 2 is allocated to P4. So available instance of C is 2. Okay, and this max matrix shows the maximum need of the process in near future. Okay, so how we can apply this safety algorithm to find out the safe sequence of the process and to satisfy the request made by the process, that we are going to see in next session. Okay, so this problem we are going to solve by applying Banker's algorithm in next session. So these are the references.